All right, welcome. Today, we're jumping right in with a consultancy-style deep dive. We are laying out the complete engineering blueprint to electrify a cement mixer's drum drive. And let's be clear, this isn't just some minor upgrade. We're talking about a fundamental strategic shift in how these construction vehicles work. We're going to go from a high-level concept all the way to a fully specified, ready-to-build system. Okay, so here's how we're going to tackle this. First, we'll hit the big picture, the strategic why behind going electric. Then we'll break down the anatomy of the system itself. From there, we'll get into the nitty-gritty, specifying the power core, defining how it operates, and then crucially, architecting for functional safety. We'll wrap it all up with a clear winning design philosophy. It's a straight line from here to a finished product. So first things first, why are we even talking about moving away from those old, tried-and-true hydraulic systems? Well, the simple answer is that the old tech has pretty much hit a wall. This move isn't just about being green. It's a strategic necessity to get past the fundamental limits of the old way in terms of efficiency, control, and, of course, operating costs. And this slide just lays it all out, plain and simple. I mean, look at this. Traditional hydraulics literally waste more than half their energy as heat. We're talking 40 to 50% efficiency. Pathetic, right? And the drum speed is stuck, totally coupled to the engine's RPM, which is just wildly inefficient. Now look at the electric drive. Over 90% efficiency. Complete freedom to run the drum at whatever speed you want, and you get to recapture energy with regenerative braking. It's a night and day difference in both performance and what it costs to run. Okay, so we see the advantages. Now, let's look at how all those pieces come together to form a single cohesive system. We're going to zoom out and look at the high-level architecture. The master plan that brings all the components together into one intelligent unit. So this diagram right here, this is our blueprint. It's built on 3 core pillars. Over on the left, you've got your hardware safety mechanisms, things like the high-voltage interlock. Right in the center, that's the brain, the motor control unit, or MCU, running all the smart control algorithms. And on the right, you have the safety state machine. That's the part that decides what to do when something goes wrong, moving the system from normal operation to a safe shutdown. It's a complete design with safety baked in from the very start. Now, to get a project like this done right, you have to draw some clear lines in the sand. So for our team, the focus is squarely on the drum drive system itself. That means the motor, the controller, the gearbox, the cooling system, and all the harnesses. So what's not in our scope? The main vehicle drive, the battery pack, and other chassis systems like brakes and steering. Having that clarity is absolutely crucial for staying focused and getting this done efficiently. All right, now we're getting to the real heart of the machine. The performance of this entire system really hinges on the specs of the motor and its controller. And these numbers you're about to see, they're not just arbitrary. They come directly from the toughest, most demanding, real-world conditions this vehicle will ever have to face. So we've specified a permanent magnet synchronous motor, or PMSM for short. And why this one? Well, because its characteristics are basically a perfect match for a cement mixer. It gives you incredible torque at really low speeds, which is absolutely critical. It's super efficient during those long, slow, agitating cycles when you're driving to the job site. And honestly, it's just a tough, sealed-up unit that's perfect for a brutal construction environment. Now this number, this is a big one. 1,200 Newton meters of peak torque. This is the raw, brute force you need for the absolute worst-case scenario. We're talking about breaking loose a full drum of concrete that's started to set up, or just starting that same heavy load from a dead stop on a really steep hill. This isn't a nice-to-have, it's a non-negotiable performance requirement. And backing up that massive torque is 125 kilowatts of peak power. Now, this isn't for just cruising down the highway. This is the muscle you need for short, intense bursts, like when you're loading up at the plant at high speed or dumping the concrete fast on the job site, where every minute costs money. This power makes sure the system can keep up when things get intense. And this thing has to be built to last. The required design life is at least 30,000 hours. To put that into perspective, that's like running the machine 8 hours a day, every single day, for more than 10 years. This is not a passenger car part, it's a piece of heavy industrial machinery, and it has to be designed for extreme longevity. Finally, let's talk about a small component choice that has huge implications. The position sensor must be a resolver. An optical encoder, with its delicate little glass disc and fragile electronics, it would fail almost immediately in this kind of environment. A resolver, on the other hand, is basically just a set of transformer windings. It's practically indestructible, and it couldn't care less about heat, vibration, or all the concrete dust. For reliability, it's really the only choice here.
Okay, so we've got the hardware specified, but the best hardware in the world is just an expensive paperweight without the right software and control logic to make it smart. So now, let's look at how this system actually behaves, which is defined by a few distinct operational modes, each one optimized for a specific job. So the Sister works in three main modes. First up is charging mode. You get high-speed reverse rotation to load materials as fast as humanly possible. Second, and this is where the genius of the electric system really shines, is agitating mode. It's a constant, super low-speed rotation while the truck is driving, but it's completely independent of the truck's speed. This saves a massive amount of energy. Finally, discharging mode. That's precision forward rotation with variable speed control, letting the operator put the concrete exactly where it needs to go, all while recapturing energy every single time the drum slows down.
But here's a really cool advanced feature we're specifying: active damping control. So get this. By watching for tiny little changes in motor torque, the MCU can actually feel the concrete sloshing around inside the drum. And once it knows that frequency, it can inject a tiny counter torque to cancel out that sloshing motion. This is a huge deal. It dramatically reduces stress on the gearbox and makes the whole truck more stable on the road. It's a total game changer for durability and safety. This brings us to what is, without a doubt, the single most critical piece of this entire design: functional safety. We are putting a high-voltage, high-torque system on a vehicle that operates out in public on crowded job sites. Making sure it's safe isn't just a good idea, it's a mandate, governed by some really rigorous international standards. And that's really the fundamental question we have to answer, right? How do you prove, with engineering certainty, that this system is safe? How do you prevent a worst-case scenario, like an accidental concrete spill on a busy highway or an uncontrolled spin on a job site? Well, the answer isn't to just cross our fingers and hope for the best. It's a formal, structured process called ISO 26262. And based on our analysis of all the hazards, we've determined this system requires what's called an Automotive Safety Integrity Level of C, or ASIL-C. That target dictates a really high level of rigor that we have to follow in our entire design and validation process. Now, what's so cool about this slide is how it visualizes that whole process. This is what we call a traceability diagram. It shows an unbreakable chain of logic, starting from a big, high-level safety goal on the left, like prevent the drum from spinning when it's not supposed to. That goal gets broken down into specific requirements, which are then built into the hardware and software. And finally, everything is proven with specific test cases on the right. Every single link in that chain has to be documented and verified. And this table gives you a perfect real-world example. So the hazard is an accidental drum reversal that spills concrete everywhere. The safety goal, then, is to prevent that unintended rotation. So how do we do it? Well, with specific hardware fixes, like a high-voltage interlock and an e-stop, and also with specific software fixes, like constantly monitoring the commands and implementing a safe torque-off function. This is exactly how you turn abstract safety goals into real, concrete engineering solutions. So after digging into all these technical details, from torque specs to safety architectures, what's the one guiding principle that should drive every single decision the engineering team makes? What's the North Star for this project? It comes down to this. The key thing to remember is that we are not building a drivetrain for a passenger car. We're building a unique kind of hybrid. So the design philosophy has to be a marriage of two worlds. You need the rugged, bulletproof reliability of industrial machinery combined with the sophisticated, process-driven, functional safety of modern automotive electronics. Every design choice has to be seen through that lens. So we've laid it all out: the strategy, the architecture, the specifications, and the safety case. The complete blueprint is right here in front of you. The only question that's left is for your team. How are you going to take this plan and engineer the future of construction?